Hi, everyone. Today I'm going to talk about how we can use user activity data, but in a bit different way. Today, almost every website and every mobile app collect every click, like, share, play, buy, or any other interaction between the users and the items. And basically, there are two main reasons we collect this kind of data. The first is to improve our platform. Internal analytics, BI reports, A/B testing, and so on. And the second common use case is to train and develop different recommendation engines that will help the users find the right content on the right item we have to offer. So today I'm going to talk about a third option or third use case to use exactly the same data, but we were going to use it to extract features that will help you to enrich or add more labels to the items you have in your database. So to give you some context and background, let's first say a few words about what we actually do at SimilarWeb. So SimilarWeb provides traffic, engagement, and other metrics for every website and every mobile app in almost every country. In simple words, we can say that our platform, the SimilarWeb Pro, is quite similar to other analytics services like Google Analytics, for example. But the main difference is that in our platform, you can get data for every website you want. For example, in this case, my query was for NBA.com. And I also filtered the data for United States. And here you can see our estimation for the total amount of traffic or total visits for this specific site in a specific time frame. You can see our estimation for the traffic share, or the split between desktop and mobile web traffic. And on the right, you can see our estimation for all the other standard engagement metrics, the bounce rate, time on site, pages per visit, and so on. And if you look on the menu on the left, you can see that we actually have much more data about this specific site. We have data about the traffic sources, the referrals, the keywords, the display ads, and many other interesting stuff. So about a year ago, the product team came to us, the research and data analysis team, with a request for a new feature, the website demographic. They basically want us to start and estimate the gender distribution and age distribution of each website we have on the internet. So today I'm going to start my presentation by explaining how we develop an algorithm to estimate the gender distribution of each site. And again, for the NBA.com example, you can see their estimation is 76% male and almost 24% female. So obviously, in order to develop this new feature, the first thing we need is data. So at SimilarWeb, we have many different data sources. But for this specific algorithm, we decided to use two main data sets. The first data set is our international panel with millions of users in almost every country. Users that use one of our application or one of the application of our partners, and we just track and collect the browsing activity of these users. And the second data set is our learning set. We have around 50,000 websites that share with us their direct measurement data. So for this small subset of websites, we do know the actual gender distribution. So it may sound pretty straightforward to estimate the gender distribution of a site. We can just, for each website in our panel, we can just count the number of males, count the number of females, and basically get the gender distribution. And then we can even use the learning set to fix the bias in the panel or improve the estimation in different ways. But the big challenge or our main problem is the fact that our panel is completely anonymous. We don't collect any data about the user. So for each user in our panel, we have some unique identifier that allow us to track the activity of the user over time. We know that a specific user visits website A, website B, and website C, but we don't have any other information about the user. We don't collect any information like name, age, gender, email address. We don't have any kind of this information. So we can't just count the males and the females in our panel since we don't have this information. So I have to admit, at the beginning, it was very challenging to find a way to actually estimate the exact gender distribution of each site without knowing anything about the gender of the users we have. So at the end of the day, we came up with an idea, and here's an example for our idea. Let's say we have website A. In our first data set in our panel, we see 100 users that visit website A. And from the second data set, from our learning set, we know that the gender distribution of site A is 80% females, and 20% males. So in this specific case, we actually can say that in this orange bag of site A, we have 80 females and 20 males. We can't say for a specific user in this bag if he's a male or female, but we know that we have 80 females and 20 males. So let's say we have another website, website B, and it's a smaller website with less traffic in our panel, and we see 90 users that visit website B, and website B is not in our learning set. So we don't know anything about the gender distribution of site B. But if you can see on the left, all the users from the diagram on the left, all the users who visit website B also visit website A. So if you take a moment to think about it, we actually can say that the gender distribution of site B is between 77% and 88%. Because we get the lower bound if we take from our orange bag of site A, we take the 20 males and add 70 females, and then we get the 77%. And we get the upper bound if we take all the 80 females we have in our bag from site A and just add 10 males, and then we get the 88% females. So actually, from this example, you can see that we can say something about the gender distribution of site B only based on the overlap between site B and site A. And this is basically going to be our approach or our idea to solve the problem. We will estimate the gender distribution of a site based on the engagement or the user overlap with the other sites we do have in our learning set. So the next thing we did after we decided to go with this idea or this approach was to take the data we collect from our panel and put it in a matrix. We call it the panel matrix. And it's just a matrix with all the sites and all the users. And we say that the matrix P, the panel matrix, ij is 1 if user j visit in website I. And otherwise, Pij is going to be 0. And obviously, we have millions of sites and millions of users. So the dimension of the matrix P is very large. And P is obviously a very large sparse matrix. You might recognize this kind of matrix for developing a recommendation engine or running some collaborative filtering algorithm. So it's kind of the same structure of metrics. So the next step after we created this metric was to find a way to reduce the dimension of the matrix P or extract feature from the matrix P and to get the matrix F. So instead of having a matrix with all the sites and all the users, we want a matrix with all the sites and some k. Obviously, k should be a very small number. So it's not a new task to extract feature or to reduce the dimension of a matrix. And we actually tried several existing algorithms like PCA, ALS model, Word2Vec, and so on. But unfortunately, none of the standard algorithms could solve our problem. First, we had a lot of problems with the scale of our data. It's pretty hard to train a model like Word2Vec with millions of users and millions of sites, or ALS model, again, with millions of users and millions of sites. But the main problem after we analyzed the results of all the standard algorithm was the fact that all the standard algorithms reduce the dimension of the matrix P without taking into account our problem. Or in other words, we don't have any option to tell the algorithm, please reduce the dimension of the matrix in a way that will help us to solve the gender distribution problem. So this is exactly going to be our solution, an algorithm that we actually can tell him, please reduce the dimension of the matrix in a way that is optimized to solve our specific problem, in a way that is optimized to solve the gender distribution problem. So after some research, we came with our algorithm. We call it interaction-based feature extraction. And now I'm going to describe the algorithm step by step with an example. So in the first step, which is pretty specific for the gender distribution case, we take our learning set and we convert it to a matrix, D1, in the following way. We decided to split the gender percentile or male traffic share to k buckets. In our case, k is going to be 10 for simplicity. So we have 10 buckets. The first bucket represents website with 0 to 10% male traffic share, 10% to 20% male traffic share, and so on. And then we just map each value from the learning set into an indicator vector. For example, in website A, we have 73%, so we get vector of zeros, and we put one in position number 8. And for website B, we have 26 male share, so we put one in position number 3. And the dimension of this D1 matrix is obviously all the sites we have in our learning set and k, the value we choose, is a hyperparameter of the solution. So let's put the first matrix. Here we have the matrix D1 of all the websites from our learning set and the indicator vector we just created. And now we're going to build the flow of the algorithm from right to left. So in the next step, we create another matrix, D2. It's quite similar matrix to the panel matrix, but in this case, it's a matrix of all the users, but only the sites we have in our learning set. And again, we say that this new matrix D2, ij will be 1 if user I visit website j. Otherwise, the matrix, the D2 ij will be 0. And the dimension of this D2 matrix is all the users we have and all the websites we have in our learning set. And the next step is just to multiply the matrix we created in the previous step with this new matrix. So we multiply D1 and D2, and you get the matrix D. And if you play with the dimension, you can see that the dimension of matrix D is all the users and k, the number 10 we choose at the beginning. And one more extra step we had to do here is to normalize each row. Now it's a user to 1. Since each user visited in a different number of sites in the learning set. One user may visit 3 sites, another user may visit 10 sites. So we had to normalize all the rows to 1. So here you can see it. We have the matrix from the previous step. We had the second matrix, the D2. We normalize each row, and we get the matrix D. And in the last step of the algorithm, we just multiply the matrix D with the matrix P of the panel, the matrix we created at the beginning, the matrix of our panel. And you can see that the dimension of the F matrix is going to be our feature matrix, is all the sites and k. This actually is the output we wanted. And here again, we had to normalize each row. In this case, it's a website one, because we want that the scale of the features of all the websites will be the same. So here we have we multiply with the matrix P, we normalize each row, and we get our feature matrix. Now, let's see the actual results of the algorithm. Here you can see the features we got for google.com. You can see that at the bottom we have F1 to F10. Again, because at the beginning we choose a k to be 10. If it was a different number, so we had different number of features. And this is the values we get for google.com. Now, in case of google.com, we know from our panel that all the users that in our panel actually visit google.com, or almost all the users visit google.com every month. So we actually can say that the gender distribution of Google should be very close to the gender distribution of the population. We don't know exactly the number, if it's 50-50, 60-40, 40-60, but it should be very close to the right or the exact distribution of the population. Now, if we take the features we got for NBA.com, you can see that we have higher values on the right, the side that represent high male traffic share, and we have lower values on the left, where the side that represent low male traffic share. So just from looking on the features, we can understand that in NBA.com we have more males than we have in Google. We don't know yet the exact number. It can be 70% or 80%, but we can understand it only from looking at the features. Now, if we take another website, like Sephora, for those of you who are not familiar, it's a company that sells beauty and cosmetic products. So we can see exactly the opposite. We have high values on the left side and lower values on the right side. So in case of Sephora, we actually, only by looking on this graph, we can say that, again, if Google is 50% male traffic share, so Sephora should be 20% or 10% or 30%. But this is what we get only from the feature. Now, obviously, the next step, once we have features for all the websites, we can just take any regression model and use the learning set again to train a model and predict the results for all the other websites we want to get the gender prediction for. And here you can see the results. Here are the results of our algorithm. Each blue dot is a website. And at the bottom of the X, you can see the value from the learning set. Y is our prediction. And if you look on the trend line, you can see that the slope is very close to 1. So we are not biased to males or females. And also the correlation is pretty good. So we use this algorithm to solve the gender distribution problem in SimilarWeb. And after it was a great success, we even use it to solve other problems like the age distribution and website classification and other internal problems. But the question is if we can expand the algorithm to solve problems in other domains. I mean, maybe it works only on our specific data or our panel for some reason. So in order to test or answer this question, I took a database of movies. It's called MovieLens. It's a database of movies, users, and ratings, explicit feedback rating. Each user had to put a rating between 1 to 5 to each movie. And it also contains some metadata about the movies. We have a list of 18 genres: action, adventure, animation, children. And for each movie, we might have one or more labels. So if you take a closer look on the files we actually have in this data, so the first file is the ratings. So we have user ID, movie ID, and the rating. And this file is actually quite equivalent to our international panel. Instead of users and sites, in this case, we have users and movie and some rating. And if you look at the second file, it's the movies. So again, we have the movies and we have the list of genres. And we can just convert each list of genres into a vector of 18 values because we have 18 labels and put 1 or 0 in the right position. So this file is quite equivalent to the learning set we had for the sites. So what I decided to do is to take the learning set of the movies and split it 50-50 to train and test. And you try to use the train data and to see the results, how it predicts the labels of the test set. Some simple cross-validation. So here you can see we just put the data from the movies as is on our algorithm. On the right, we have the train set movies and the 18 labels. We have the matrix D2 with all the users and the movies we have in our train set. And on the left, we have just a matrix of all the movies and all the users. For simplicity, I put the ratings as is. I might try to normalize them per user or do some manipulation, but for simplicity, I decided to put the ratings as is from the data in our matrix. So here you can see the results of the features we got for the movies. In case of the movies, we don't have a movie like Google that everybody watched. So in this case, the blue line represent the average value of each feature across all the movies we had in our train set. And if you look at the orange line, it represents the movie Armageddon. You can see that compared to the average, we got very high values in action, sci-fi, and another labels that, and if you're familiar with the movie, you actually say that these labels are pretty make sense. And for another movie, the gray line, it's Dumbo. So we got higher values again compared to the average for animation, children, and musical. And again, if you are familiar with the movie Dumbo, these labels are pretty make sense. So after we got these features from our algorithm, we just go and train a classifier for each label of movies we have. And here you can see the results. For animation, you can see that we got a pretty high accuracy. For adventure, we also got some reasonable results. But the overall accuracy was around 83%, which is pretty good. And the bottom line is by using our algorithm of interaction-based feature extraction, we got very high accuracy, both in the gender problem, the internally and similar for the age distribution, website classification, and other problems. And also you can see that in the movies we got pretty good accuracy. We got features in a very low dimension. In case of the gender, we got 10 features, movies was 18 features. It's pretty low dimension of features. The algorithm is very scalable. There is no some gradient descent or any other optimization process in the algorithm. So we just multiply 3 matrices and get the features. And also the algorithm is very simple and explainable. So if we're, for example, we are running the gender distribution algorithm for several months, and if for a specific one we get a weird result or strange result for a specific site, we can just go and analyze the process step by step quite easily and understand why we got this specific result for this specific site. And that's it.
Are there any questions?
Okay, I didn't understand the problem setup. So how did you? You said at some point that you don't know the genders of the users.
Right.
What do you know about them?
I have some unique identifier of the user, and I know the activity of the user. The user visit in Facebook, and then Google, and then some news site. This is the only information we have about the user. We don't have any other information. We don't know his name, age, gender, nothing. We have some persistent unique identifier, random one, that allows us to track the activity of the same user over time, but beside that, we don't have any information about the user.
But then how are you? Oh, so yeah, but you do have a training set which consists of where you do know the gender, right?
We have a training set for the websites, not for specific users. This was the old idea that we
Okay, so you have
extrapolate
one
or
website where you do know the gender,
Yeah.
and then you have these other websites where you don't know the gender.
Yeah. So
And
based on the overlap or the engagement of the users from the site I don't know, I just analyze the activity of the user of this specific site with the site I know, with the sites I have in my learning set, and then I create the features. This is the idea of the algorithm. Yes.
So what was the you had a K by something matrix? What did the K correspond to?
Let's go back. You're talking about this matrix?
Yeah.
So we have our learning set, just a list of sites and their a learning set list of sites and their value we get from our learning set. For example, for website A, we have 73% male traffic share, and for website B, we have 26 male traffic share. This is just
how did you? But now you do know the traffic share. So where did you get that information from?
For the websites, we do know. We have, as I said, we have about. There you go. We have about 50,000 websites that share their direct measurement data, Google Analytics or other internal analytics they have, and from that we can know the gender distribution of the sites.
Okay.
Hi. Really nice work around the matrix multiplication. So I just wanted to check, like, if you want to explain this thing to some non-data science guy, how would you actually try to explain? So, like, let's say in PCA case, we try to explain like we are just projecting the features in another dimension where you have more variance, so that, like, let's say you can still able to explain all the variance with less dimension. Yeah. But here we projected, I guess, some hidden feature from the user level, either at movies or websites, to predict their gender or, like, let's say, the gender distribution. So how to build some simple definition which we can explain to others?
A simple definition. Again, it's very close to recommendation engines that we know from a specific movie what other movies you may like based on the interaction between the users. So we would just use the same user activity to tell. We kind of recommend the gender distribution for the site based on the overlap of its user with the other sites. This is basically the concept of the algorithm. And one more thing is algorithms like PCA or metric factorization, they actually try to take all the information we have in our panel metrics and find a representation in a lower dimension. In our case, we actually didn't take all the information from panel metrics. We tried to extract the relevant information to solve our specific problem, which in this case was the gender distribution, but it's more like a feature extraction, not dimension reduction in our case.
So you said you got 83% classification accuracy. When you got the model to achieve that, did you do anything to capture user ranking bias? When you applied the same approach to movie lens data set, you used the user rankings in a similar way to the web page visits from your original data set. But yeah, user rankings can be, some user might be ranking higher than the others. It can be high rankers and that can be low rankers. So did you do anything to address this issue?
No, as I said, in our panel metrics, when we solved the gender distribution problem, we just put 1 or 0. We didn't put a rating for the specific case. And I mentioned when I talk about the movies example that I could do something more advanced than just put the ratings as is. But for simplicity, I just decided to put it as is. You are correct. You are right. We obviously need to do something to normalize the data per user or something like that. But in the case of the gender distribution, you just put 1 or 0. So.
But no, you got 83%
Yeah.
for movie lens,
Yeah.
right? And then
In
you
that
got
case, we
that
didn't-
without any normalization.
No.
Okay, that's yeah. Thanks.
It's related to his question. Did you start using a Lime or Shap for explaining or recommend the features and the age or movie to explain the recommendation or find the right features that tell us that is male or female or he likes this movie?
I'm not sure.
Shap or Lime, projects that's using game theory or something like that. If not familiar, it's okay.
No.
Okay, thank you.
Is the implementation of the algorithm available somewhere? Or, and another question is this applicable to non-sparse matrices as well?
We didn't try it on other use cases. Basically, it was an algorithm we developed for our own needs, but we didn't try to solve it. We didn't have other data set to play with, so it's a good idea to try. You know.
Yeah, I wanted to ask, if I understand it correctly, you are predicting the gender distribution on the website level.
Yeah.
If I understand it well, then probably as a byproduct, you are also can get a prediction on the user level. If what's the probability that he's a male or a female? Does it work that way, or do you use it in this way as well?
No, because if you look, I have some extra slide here, I think, at the end of the presentation. Okay, if you look at the data per specific user, if you just look at the D metrics, the intermediate of our algorithms, you can see this is how the data we get per specific users. So user number 1, user number 2, you can see that the data for a specific user is very sparse and very noisy. So the accuracy we got for when we're trying to use the feature we got for a specific user was basically all the prediction was between, let's say, 0.4 and 0.6 for all the users. So we did try to use it, but as you can see, the data is quite with a lot of spikes and quite noisy.
Yeah, but this is the training data just from the 50,000?
Yeah.
But if you like you do the same approach you're using for each website, you
after the
estimate
prediction?
the gender, and then you could basically update this vector not based on just the 50,000, but actually also including your projections, then it would probably be stronger a bit, right?
We try to, you're actually suggesting that after I have the prediction for all the website, you
Yes, yes.
use my prediction as a learning set and try it again,
Yeah,
and then get the features for users. And it didn't work so well. I mean, the features were very close and it didn't work so well. And the prediction, again, for most of the user was, all the predictions were very close to 50-50 or 50% probability.
Okay, good. That was what was interesting for me. Good.
All right, last question.
Hey, great presentation. Just a question. So on the movie side, obviously we understand that the movies are comedy, etc. So you can validate your assumptions. But on the websites, have you tried to validate against first-party data to understand, okay, is this working truly or not?
So first, we obviously did some internal cross-validation when we developed the algorithm and saw that the results are matched and that we get exactly the same accuracy. And we also compare our results with some, let's say, papers or public data, and we saw that we are pretty much accurate as we see in the graph.
All right, thank you, Shlomi.